So this right here is kind of asking you to think about a compound and take this display right here, which has a legend right here, and convert this, well, at least three-dimensional object that we're looking at here to a formula. Okay, now what you can see here with this symbol is we've got nitrogen represented by these blue spheres, we've got carbon represented by the black spheres, and then we've got oxygen and hydrogen represented by the red and white spheres respectively. So in order to convert this right here into a formula, what you want to do is write out what are all of those different elements, what are their symbols. Nitrogen is N, oxygen is O, carbon is C, hydrogen is H. Okay, so let's just write it out as NOCH. Now, to use this information to kind of convey this 3D image into a formula that we're writing out here, well, is it simply NOCH? No, because there are multiple nitrogens, there are multiple oxygens, multiple hydrogens, and carbons. Okay, so let's go ahead and just count them up. So nitrogen, we've got 1, 2, 3, 4. Now what you do whenever you see the number, you're going to put that as a subscript. So I'm going to write 4. Now for oxygen, represented by these red spheres, we've got 1, 2. So I'm going to write O subscript 2. Carbon is represented by the black spheres, 1, 2, 3, 4, 5, 6, 7, 8. Carbon C8. Hydrogen, well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10. Okay, so if you were to be looking at this molecule right here and trying to come up with what is the formula for it, simply writing NOCH tells you the elements that are present, but it doesn't tell you the ratio of those elements, nor does it give you any information about the organization of those. What we've done here is we've at least improved upon that, because this tells you the number of each individual element. It doesn't give you too much information on the organization of it, but at very least we have kind of a ratio for them. So writing formulas is a very important skill to develop. And this right here, this is just kind of a rough exercise. We'll come back to these in a little while, but for the time being, just keep this in mind. Okay, now a formula describes a substance. The number, a formula can be a simple element, or a single element, or it can be a compound, multiple elements assembled together. Subscripts show how many atoms of the element before it are present in one formula unit. So if you have one copy of that molecule, how many of those different elements are there? A missing subscript means 1. Multiply subscripts outside of parentheses times subscripts inside to get the total number of atoms. So if we look at this one down here, CaNO3, we've got all of these things at play. First of all, this is going to show us we have no subscript for calcium, which that implies that there is 1 calcium. Okay, so check mark there. Next, we're going to multiply the subscripts outside of the parenthesis times the subscripts inside to get the total number of atoms. So in this molecule right here, the Ca parentheses NO3 close parentheses 2, how many nitrogens are there? Well, if we follow this rule, multiply our subscripts outside by those inside, there would be 2 nitrogen. How many oxygens would there be? Well, we take this 2 and multiply it by 3, and we get 6 oxygens. All right. Now, to apply that, how many hydrogens are in ammonium sulfide? NH4-2S. How many hydrogens? Well, we know that we've got to take the 2 outside the parentheses, multiply it by the 4, so we get 8. All right. So this calls into question a number of different skills. You have to be able to identify a symbol. So we use the name hydrogen. We didn't say H, but instead we just had to say, okay, hydrogen, what is that on the periodic table? That is H. And like I said, many of these elements are going to become kind of second nature for quickly coming up with a symbol. Okay, then we've got this quote from Sir Isaac Newton. If I have seen further, it is by standing on the shoulders of giants. And that just kind of illustrates the greatness of science, of, every generation builds upon every previous generation. Science is very dynamic. Experimental data determines what is right in science, what is correct, what is the, I guess, kind of best practice. Science changes over time as new experiments are performed and new data are taken which disagree with prior scientific concepts. An article that I'll make available to you called Put Your Faith in Science on... What you see in this slide right here is basically a demonstration of a phenomenon known as the law of conservation of mass. It was Antoine Lavoisier who kind of came up with this theory. And what we're seeing here is we have a bell jar that has underneath it a dish with phosphorus in it and a pool of water. Okay, inside this bell jar, which I believe that's a bell jar, we've got air. Okay, phosphorus is highly reactive. And what we see is on our digital balance, we have a mass of 937.4 grams. So that means the glassware plus the water plus the phosphorus, and this is a little bit tricky to wrap your mind around, but the air has a combined mass of 937.4 grams. Okay. Now, what's going to happen is that the water that is within this pool that is under the bell jar is going to make this atmosphere much more humid. And at a certain high level of humidity, well, that phosphorus is going to react. And what's going to happen is that is going to react and burn up all the oxygen that's in the environment, and this phosphorus is going to be converted to phosphorus oxide. Okay, water will rise up within this bell jar. Our oxygen has all been consumed. We have phosphorus oxide, water. Okay, so the question is, what's the mass of that whole system? That mass is still 937.4 grams. So we had phosphorus. Well, now we don't have phosphorus. We had oxygen in here. Now we don't have oxygen in here. So I'm going to write O2 down. Gone. That's what I meant to say, done and gone in the same word. So I said dawn. Anyway, so that oxygen and that phosphorus, they've both been depleted, in which case now we have phosphorus oxide, and we have a total mass of 937.4 grams within this system. So our mass has not changed at all. The law of definite proportions, devised by Joseph Louis Proust, he compared the mass composition of water, or basically the makeup of water in France, Spain, and the so-called New World, and lo and behold, water was 89% oxygen, 11% oxygen. So in a compound, the constituent elements, so that the components that make it up, are always present in a definite proportion by mass. So no matter what, if you look at water in Singapore or water anywhere else, it's still going to be H2O. It's that perfect ratio of 2 hydrogens to 1 oxygen. If you change that to make H2O2, you're not talking about water anymore. Same thing goes with copper carbonate. Here's just some data points that reflect that. Now, John Dalton came up with the law of multiple proportions, and this basically was that you can have different elements combine in different ratios. So carbon and oxygen can combine 1.33 grams of oxygen for every 1 gram of carbon. At the same time, carbon and oxygen can also combine in a ratio of 2.66 grams of oxygen for every 1 gram of carbon. So these are both combinations of carbon and oxygen. One happens to be 1 carbon to 2 oxygens, and the other happens to be 1 carbon to 1 oxygen. So this is the law of multiple proportions is true. Two elements can combine in different ratios. All right, well, I hope this is helpful, and we'll proceed on with further discussion of the periodic table in our next video. Thank you very much.